Thank you, Leon, for the introduction. My name is Brian Anthony, as Leon said, and I want to share with you a little bit today our work in learned control, or more specifically, deep reinforcement learning for reducing time to market of new products. The high-level summary of what I want to talk about today is we'll start with products. We'll talk about the machines that build those products, and we'll talk about the control signals that are informing those machines to make them sing, to make them live, to do the things that we want them to do to create products. And we'll talk about how we want to reduce the amount of time that it takes to develop new machines, but more specifically, to develop new control strategies to make new products once we have either product variants or new things that we want to make with the same machines. So products are designed to meet consumer needs. Products are as varied as our needs, everything from coffee to maybe tea, if that's your preference, to medication for inside the body, for lotions and creams outside the body, or bottled water, or bottled beverages of other sorts, or fiber optic cables for the massive need for data communications, or novel fibers for our clothing. Now, all of those products are made with machines. Machines are designed to make products. This is a coffee roasting machine, controlling the temperature and the humidity and the airflow while we're roasting beans. Or a packaging line for creating tea bags, filling the bags, stitching the bags together. Creating pharmaceutical pills, compacting the active pharmaceutical ingredient into capsules. Or putting the capsules into blister packs for then delivery to the consumer. Or wrapping our plastic bottles, or in this case, our deodorant, with plastic films before they are shipped and delivered to the store or to the consumer. Filling of bottles. Creating of optical fibers, extruding, machines to extrude fiber, or machines to extrude the apparel fiber that is relevant to our daily life. Now here is a machine, which is a sewing machine, just to give you a feeling for the motion and the properties that we are concerned with in machines that are designed to build products. All the machines that we saw, those were but frames, single frames of a very complex arrangement of intermoving parts. This is a video recording at 6,000 frames per second of a sewing machine, an industrial sewing machine stitching clothing. All of these machines take as input time varying control signals or control trajectories. And those trajectories are designed to make the machines come alive, to do the things that we want them to do. Those trajectories could be pressure and temperature and gas flow versus time, or velocity and force versus time, temperature and current versus time, position, velocity versus time, humidity, temperature, and gas flow versus time. But what happens when we have a new product, or we want to change the properties of the product? Do we need a new machine? Do we need new control trajectories? Do we have to build an entirely new machine to make these different coffee roasts? Do we have to build entirely different machines to be able to fill these different tea bags? Do we have to make entirely new machines to create an optical fiber or a polymer fiber that has varying properties along its length? New products require new machines? Hopefully not. But without a doubt, they will require new control trajectories, new signals to make them do the things that we want them to do. So the summary here of what we're talking about is we have products designed to meet consumer needs, made by machines, made by and controlled by time-varying control trajectories. A new product is introduced. We don't want to have to build a new machine. That's a very time-laborious thing. We do absolutely need to make a new control trajectory, but do we need to know the physics of the machine? Do we know all the ins and outs of the changing ways that we may want to use the machine to modify it to make this new product? What we're doing in our very interesting and I think impactful work is to, while we're making a product, to learn about the physics of operation, to learn about the physics of the machine, to learn about the physics of the product that we're making, so that when we have a new product or a new trajectory that we want to end up with, that we have already a deep understanding, a learned understanding of how the machine works. And we use that knowledge to accelerate the creation of the new time varying controlled trajectories to make our new products. That's the graphical representation. The machine learning paper version of this, where we sort of stick it into our publication, is we have an action interacting with an environment. We have rewards. So the environment is our manufacturing process. The reward is we're trying to achieve a certain quality of our product. And the agent, the machine learning, the deep reinforcement learning, is learning how to better adjust its control properties, its inputs and its outputs to achieve the reward that we want, to achieve that quality product. And our coffee example, we have signals that tell the machine what to do. The machine interacts with the environment making coffee. We observe that coffee making so that when we want to make new coffee with varying properties from what we've already made, the learned algorithm knows how the machine performs, knows how to adjust it to achieve our new desired goal. This is the machine learning framework. It's an actor-critic based approach. Many details that we can certainly talk about offline, but it's a framework building on all this massive investment that's happening in deep learning, but very much applying it to the manufacturing environment. In this last slide, I just want to share with you the examples of applications where we've currently deployed this. We've looked at advanced fiber manufacturing, so making fiber have very novel properties as it's being extruded, both in the dimensional properties of the fiber and in the materials that are input into the fiber. More recently, starting to look at coffee roasting and then packaging, pharmaceuticals, and soft robotics. And the small graph on the left is just to highlight the process by which, over time, as the machine continues to make product, it learns about the machine, it learns about the physics, it learns how to improve itself. With that, thank you for your time. I look forward to taking questions in a breakout session or at your convenience. So thank you.